Okay, so in this lecture we will now discuss differentiation in the S domain and integration in the time domain. Okay, now first let us talk about differentiation in the S domain. So if x of t has Laplace transform x of s with ROC R, then t times x of t has Laplace transform minus 1 times d times x of s divided by ds. Sometimes people will write like this also, minus t times x of t has Laplace transform of d times x of s divided by ds. Both are same, okay, with ROC is equal to R, and here also you can write with ROC R. Okay, we know the Laplace transform of x of t, and then we would like to find out what is the Laplace transform of t times x of t. What is the Laplace transform? Without going by traditional way, like you can do it like minus infinity to plus infinity, or 0 to infinity t times x of t and e to the minus st and dt. And this again you need to do the integration. It is little tedious job. So don't do that. So we have some shortcut method for calculating the Laplace transform of t times x of t. So we know the Laplace transform of x of t. Now we want to find out t times x of t. Okay. Now what you do? This is equal to integral of 0 minus to t, then t times x of t e to the minus st and dt. Now to do this integration, let me take a derivative of f of s. So this is my x of s. Take derivative on both sides. Okay, so d over ds of x of s is equal to, here also take the derivative, d over ds integral of 0 minus to infinity x of t e to the minus st and dt. So the integration is with the reference to t, and we are taking the derivative with reference to another variable s. So we can introduce this differentiation inside the integration sign. Okay, so therefore this is equal to integral of 0 minus to infinity x of t, then d by ds of e to the minus st times dt. So this is equal to 0 minus to infinity x of t minus t times e to the minus st and dt. Then this minus you can pull it outside, minus 0 minus to infinity, then t times x of t e to the minus st and dt. Now don't you see, this is the Laplace transform of what? T times x of t. On the other hand, in the left hand side you have d by ds of x of s. So therefore these two guys forms the Laplace transform pair. Laplace transform of x dash of s, Laplace transform of t times x of t is equal to minus of d by ds of x of s. Sometimes people will write t times x of t and this minus dx of s divided by ds forms the Laplace transform pair. Okay, so when you multiply a function x of t by time t, Okay, as far as the transform is concerned, it is equivalent to the negative of the derivative of the function x of s with reference to s. So derivation is taken with respect to s. So you can see that there is a nice arrangement here. You multiply by time, multiply by t in the time domain, and you get a minus d by ds in the derivative in the transform domain. Okay, on the other hand, if you look at the previous property, if you take derivative in the time domain, then it is going to be multiplication in the frequency domain. So there is a similar relationship, except there is a negative sign. Okay, the only difference is negative sign here, and here no negative sign. That's the only difference. So it is somewhat a dual relationship. Multiplication in the time domain, multiplication in the frequency domain. Now based upon this, let me extend this result. So this result, we have t times x of t forms Fourier transform pair with d times x of s divided by ds. Suppose I take t squared one more times, t squared of x of t. If you follow the same procedure, then it will be again minus d by ds of the Laplace transform of t times x of t, right? So t times x of t, the Laplace transform is minus d by ds of the Laplace transform of x of t. Similarly here what you do, you find out this guy you can write as t times of x of t, like this you can write. Okay, now you find the Laplace transform of this, and this we know here, you can substitute there, minus d by ds of the Laplace transform of t times x of t is minus d by ds of x of s. Now this minus and that minus both will get cancelled, so d squared over ds squared of x of s. So in fact what you do is, instead of writing like this, there are two minus signs, 1 and 2. So you can put minus 1 the whole squared. So this is t squared of x of t. If there is a square and here also square and here also square, then if it is cube term x of t, then this becomes minus 1 whole cube, same 3, then d2 3 divided by ds 3 x of s. Okay, all the time functions, we are assuming that these are causal functions. That means what? T is greater than 0, the function is non-zero. Okay, so therefore you can simply extend this for t power n. Okay, now you can keep on continue this. T to the n has Laplace transform minus 1 whole to the nth derivative of x of s. That's it. So that's how it goes as we take a higher and higher powers of t. Okay, the Laplace transform goes in this manner. So let us take a simple example. We know the Laplace transform of u of t. What is the Laplace transform of u of t? It is 1 over s. Now what happens if I take the Laplace transform of t times u of t? It is very simple. Minus d by ds of 1 over s, which is 1 over a squared. Okay, what is t times u of t? If you recall, this is your unit ramp function r of t. Therefore r of t, if you take Laplace transform, then it becomes 1 over a squared. Okay, because t times u of t is indeed r of t. So the Laplace transform of a ramp function is 1 over a square. So we can extend our Laplace transform pairs like this: t squared, then t cube up to tn like this. So the result goes like this. If you take del of t, the Laplace transform is 1. U of t, the Laplace transform is 1 over s, and r of t, the Laplace transform is 1 over s squared. If you take some constant k, Laplace transform is 1 over s. Or you can take constant times u of t, then also the Laplace transform is 1 over s. These are the some important results that one should keep in mind. Okay. Now let us consider another example. Suppose I have e to the minus at times u of t. What is the Laplace transform this? This is 1 over s plus a. Now suppose I multiply this guy by t. Okay. Then t times e to the minus at and u of t. How do you find out the Laplace transform? By definition, you can say 0 minus to infinity t times e to the minus at, e to the minus st and dt. Now this is a lengthy integration, somewhat lengthy integration. Okay, you have to find out u dv, then uv minus integral of v du and substitute the limits. So it takes little bit amount of time. So instead of doing this in direct method, indirectly you can find out. What is that? Using the property by differentiation the time domain. So you multiply in the time domain e power minus at and u of t, that becomes negative derivative of the Laplace transform of x of s. So minus d by ds times what is x of s? 1 over s plus a. If you differentiate, then you will get 1 over s plus a the whole squared. Suppose if you put t squared times e to the minus at times u of t, then it becomes, if you do this work, then 2 divided by s plus a whole cube. So in general, if you keep on continue this, then t to the n e to the minus at u of t becomes n factorial divided by s plus a whole power n plus 1. See, here there is a power of 2, that 2 becomes same 2, that I can put 2 times 1. So this is 2 factorial. In the denominator you have 3 power plus 1. So that's why if you have n here, this becomes n plus 1 and this n becomes n factorial. Okay. So in other words, we need not to remember the Laplace transforms for t multiplied functions like this. Okay. Only remember what is the Laplace transform of e power minus alpha t times u of t, or in terms of u of t. That is enough. If you know the basic formula of u of t or e to the minus at times u of t, that is enough. Using the properties, you can easily find out. Okay. Now let me take one more example. Consider the Laplace transform x of s is equal to 2s squared plus 5s plus 5 divided by s plus 1 the whole squared times s plus 2, and the region of convergence ReL of s is minus 1. Now apply partial fraction expansion for this, then we can write this as 2 by s plus 1 the whole squared minus 1 divided by s plus 1 plus 3 by s plus 2. Okay. Now since we said ROS is the right side of minus 1, that means right side of minus 1. So the inverse transform will be multiplied by u of t. And the poles are located at minus 1 and minus 2. Okay, I have multiple poles at minus 1. 3 poles are there at minus 1. Okay, so in this point I have 3 poles, minus 1 comma minus 1 comma minus 1. So this is my region of convergence. So when I say ReL of s is greater than 1, that means it is a right sided sequence. Whatever you take the Laplace transform, that will be multiplied by u of t. Now in the denominator you have square term. If it is square term, then this is The first one is you can write as 2 times 1 over s plus 1. What is s plus 1? S plus 1 is e power minus t. If square comes, then t times. So 2 times t times e power minus t. The first term is. And of course you multiply by u of t. Why did I multiply by t? Because there is a square term here. Minus this term 1 by s plus 1. So e power minus t u of t. And this one becomes plus inverse Laplace transform I am taking. Okay, this is my x of t. E power minus 2t times u of t. That's it. So simply you can find out the inverse Laplace transform if you know the differentiation property in the frequency domain. That will be equivalent to multiplication by time in the time domain. Okay. So the next property is integration in the time domain. This is also very important property. Integration in the time domain. I think this is the fourth property. The first property is linearity, and second one is differentiation in the time domain, and third one is differentiation in the frequency domain, S domain, and the fourth one is integration in the time domain. And this property says if x of t has Laplace transform x of s with the ROC is equal to R, then integral of the signal minus infinity to t, or you can consider because we are talking about a unilateral Laplace transform, right? Even you can extend this to bilateral Laplace transform also. For the time being, let us assume 0 minus x of tau d tau as the Laplace transform of 1 over s x of s with the ROC containing R intersection real of s greater than 0. This real of s is coming from this whole expression. Okay, now let me say this is for bilateral Laplace transform, so I'll put a minus infinity. Okay, this property is the inverse of the differentiation property. Okay, it can be derived using the convolution property presented in the previous lecture, like integral of minus infinity to t x of tau d tau is equal to same argument we did this for Fourier transform also, minus infinity to plus infinity, or you can say this is u of t convolved with the x of t, right? So I can write this as minus infinity to plus infinity x of tau u of t minus tau t tau, and if you simplify this, one second, okay, one second. Anyway, that property we will discuss a little later. This we can write as u of t times x of t, and in the transform domain it becomes multiplication. Okay, so the Laplace transform of u of t is 1 by s, and the Laplace transform of this guy is x of s. So this is x of s divided by s. Okay, so this is for bilateral Laplace transform. Now let us consider what will happen for the unilateral Laplace transform. The same property, slight changes will be there between bilateral Laplace transform and unilateral Laplace transform. Okay, now in the unilateral Laplace transform we will consider 0, the limit only changes, 0 minus to t x of tau and d tau, and say this is indefinite integral, minus infinity to it is indefinite integral. Now here I have definite integral. Okay, suppose let us say x of t is a current. Okay, and this current now let's say x of t is a current. Then what we are doing is, by integrating the current from, when you integrate the current you get a charge, right? Basically that's what we mean by integrating the current. So you take a copper wire and there is a flow of current I. That means what? Number of coulombs per second. So if you integrate this current over a period of time 0 minus to t, then you will get a total charge. So basically when you integrate a current x of t and dt from 0 minus to t, that means it gives the charge, total charges. Okay, you get the charge. So we often find it convenient to consider the charge at a point of time t as an initial charge plus some additional charge that is carried by the current in the point from 0 minus to t. Okay, so therefore we will think this x of t is current, and if you integrate over a finite interval, then we are talking in terms of this whole thing becomes total charge. Okay, so suppose you have a current source and you close the switch at t equals 0 minus. Okay, so you have an inductor, then capacitor, then resistor, like this. Now before you close the switch, there is certain initial amount of charges are accumulated in the circuit or stored in the circuit. Okay, so let's say from minus infinity to 0 minus 0 minus x of t and dt. So this is the charge stored before t is less than or equals 0 minus. Okay, now let me denote this guy as x inverse of 0 minus, like this. What does it mean? This minus indicates integration. This is the initial value of this integral. Okay, x to the minus 1 of, like this. Therefore your integration from okay, so integral of x of t and dt is equal to 0 minus to t, then x of t dt plus the initially stored charges, that is x minus 1 of 0 minus 1. Okay, now what is this? This is the value of the integral between the definite limit 0 minus to t. So this is how we can put the indefinite integral in the form of definite integral. So on the left hand side we have indefinite integral minus infinity to t. What is this? Indefinite integral, and here I have definite integral. So this guy represents minus infinity to 0 minus. Now in order to find the Laplace transform of this guy, let us find the Laplace transform of, in these two quantities. I have two quantities, let's say this is 1 and 2. There are two quantities. So first let us find out the Laplace transform of the first quantity. Okay, first expression. What is the first expression? 0 minus 2 t x of t times dt. Let me call this guy is equal to, let's say, some function g of t. Then we know straight away that g of 0 minus. What is g of 0 minus? See, this t is here. If you put 0 minus, then this is 0 minus, the upper limit also 0 minus x of t and dt. What is this value? This value is going to be 0, because we are taking the integral between the two limits, those two limits are the same, 0 minus to 0 minus. Therefore, this is equal to 0. And further, let limit as t goes to infinity of g of t times e power minus st equals 0. Okay. Suppose g of infinity g of infinity, or let me stop at this point, then we will come back to this point little later. Okay. So I can write g of t like this: g of t is equal to 0 minus to t x of t and dt. If we differentiate both sides, differentiate a left hand side and right hand side, then g dash of t is equal to, if we differentiate, the differentiation and integration will get cancelled, then you will get a x of t. Okay. Now using this, the Laplace transform g dash of t, what is this Laplace transform of g dash of t? Let me take g of t. G of t is equal to integral of g of t times, by definition, e to the minus st and dt, and the limit is 0 minus to infinity, by definition of the Laplace transform. By definition of Laplace transform. Okay, now let's do this integration by parts. Okay, so this is going to be g of t times e to the minus st, and the limit is 0 minus to infinity, plus integral of g dash of t, if you within the integral g dash of t, then 1 over s e to the minus st and dt. Now let us evaluate this guy. What is the upper limit? At the upper limit, when this is t equals 0 to 0 minus to t equals plus infinity. When t goes to infinity, then g of t times e to the minus st goes to 0. Why? Because that's how we defined the Laplace transform. Okay, we are taking the value of g of t. Okay, this g of t will be Laplace transformable if and only if you multiply g of t by e to the minus st and allow limit t goes to infinity, then that should be equal to 0. Otherwise it will not converge. Therefore upper limit becomes 0. What about the lower limit? Lower limit will be g of 0 minus times e to the 0. Anyway, e to the 0 is limit t goes to 0. This is g of 0 minus times 1. What is g of 0? Just now we got g of 0. Where is it? Yeah, it is here. G of 0 is equal to 0. Therefore, in this expression, the first part of the expression, in this expression, the lower limit is 0, so upper limit is 0 and the lower limit also 0. 0 minus 0 and plus the rest of the integration. This 1 over s is a constant, you can pull outside, g dash of t e to the minus st and dt, and this g dash of t comes from your integration by parts. So u dv equal to uv minus integral of v du. Okay, therefore this is 1 over s integral of, what is g dash of t? By the way, g dash of t is equal to x of t. So x of t e to the minus st and dt, this guy. Now the limit is, by the way, this limit is 0 minus to infinity, and this also 0 minus to infinity. I forgot to put it here. The limit is coming from there, from the definition of the Laplace transform. Okay, So don't you see, this is the definition of the Laplace transform of x of t. Therefore 1 over s times x of s. Therefore the Laplace transform of g of t is equal to this one. What is g of t? G of t is integral of 0 minus to t x of tau d tau is equal to 1 over s times x of s. This is the first part. If you go back and see, so this first part, the first part we defined a g of t. Now let us find the second part. What is the second part? Second part is x to the minus 1 of 0 minus, and by the way this is constant. Okay, so this is the amount of charge stored in the circuit before you close the switch at t equals 0 minus. See, you have a circuit and you are pumping some current and you are closing the switch at t equals 0 minus. Before you close the switch t equals 0 minus, then some amount of charge will be there in the circuit. Okay, that's charge we denote by x minus 1 of 0 minus 1, and this charge is constant. That is why we said it is a constant. So if you take the Laplace transform of a constant, then Laplace transform, then x to the minus 1 of 0 minus divided by s. Constant will be multiplied by 1 over s if you take the Laplace transform. So the Laplace transform of the indefinite integral minus infinity to t x of tau d tau is going to be x of s divided by s plus x of minus 1 0 minus divided by s. That's it. Okay. On the other hand, if you want to take the Laplace transform of the definite integral, this is the what? Laplace transform of the definite integral. Okay. Now therefore 0 minus to t x of tau d tau, then this Laplace transform becomes x of s by s. That means the initial value of the integral is ignored. Okay, you are ignoring this initial value, not this s. This is the initial value. Okay, when you ignore the initial value, then this is how your definite integral looks like. So these are the two important relationship. Okay, let's say this is 1 and this is 2. Important results relating to integration in the time domain and the corresponding Laplace transform in the frequency domain, and we can make use of this. Therefore whenever you have integration, that integration becomes simple algebraic expression. So it is a boon for us. So by using Laplace transform, if we encounter integral differential equations, then that will be converted into an algebraic equations. Once you have an algebraic equation, then manipulation will be very, very simple. Okay. So now this concept can be used to capacitors. Like I have a capacitor. Let's say the capacitance is C, and current flowing through the capacitor is I of t. The voltage developed across the capacitor, let me call Vc of t. So current is entering this point, so this is positive, and leaving at this terminal, so that is negative. Okay, then what is the relation between voltage and current? Vc, let me use small letters, lowercase letters. Vc of t is equal to 1 over c integral of I of t times dt. Okay, now what is this I of t times dt? It is the charge on the capacitor. So I can write further this as, let us say, minus infinity to t 1 over c integral of 0 minus to t definite integral I of t times dt plus 1 by c the initial charge on the capacitor. Initial charge on the capacitor. Okay, that means this is your circuit, capacitor circuit. You connect a current source I of t, but you are closing the switch at t equals 0 minus. Okay, before that the capacitor has some amount of charge. That charge we write like this. Let me call that charge is q of 0 minus. So this equation, this thing becomes 1 by c integral of 0 minus to t I of t dt plus q of 0 minus divided by c. Now you can take this 1 over c commonly outside, 1 over c, then 0 minus to t I of t dt plus q of 0 minus. On the left hand side you have Vc of t. Now you take the Laplace transform. Let's say your Vc of t has Laplace transform of capital Vc of s. It's a function of s. When I put s, then it means function of s. And I of t has a Laplace transform of I of s. Then this is a constant, right? Constant becomes 1 by s. Okay, q of 0 becomes q of 0 minus divided by s. Therefore this equation becomes capital Vc of s, is equal to 1 by c multiplied by s times I of s. This is a definite integral. The definite integral comes like this, plus q of 0 minus divided by s. Now you multiply this 1 by c inside, so you will get I'm sorry, I did wrongly. It becomes I of s divided by s. So this is going to be I of s divided by sc plus q of 0 minus divided by sc. So V of s. So this equation can be represented nicely in the following way. Like you have a voltage. This is the voltage, by the way. Okay, what is this guy? Voltage. Current times admittance. What is the admittance? Current I of s times admittance is 1 over sc. So the voltage across the capacitor is I of s. This is I of s, and this is 1 over sc. And then you have the source some voltage, that this is nothing but q of 0 minus divided by sc. Okay, so this is the voltage which you are measuring between these two terminals. What is that? Vc of s. Therefore 1 by sc is the generalized impedance. What is this? Generalized impedance. And what is I of s? I of s is the current passing through the generalized impedance 1 over sc, and that will create this voltage drop. That voltage drop is I of s divided by sc. This much voltage drop it creates. In addition to that, you have this much voltage drop due to the initially stored charges on the capacitor. Okay, so I have this voltage drop. In addition, I have this initial voltage drop, initial value of the capacitor voltage. I am not this one, I am sorry. The initial voltage will be this one, and then you divide by 1 by s. So the initial voltage will be q of 0 minus divided by c. This is my initial voltage, and divided by s. So this one is the transform diagram of a capacitor in the same way as we have derived it for the case of inductors in the previous lecture. Okay, an equivalent in the parallel form, you can capacitor in parallel with the current source can also be derived. You can just rearrange this equation. Okay, so this one if you rearrange, then SC times VC of S, right, is equal to I of S plus Q of 0 minus, and I of S is equal to SC VC of S minus Q of 0 minus. You can put the same thing in the parallel form also. You have a capacitor and then your current source is coming in the opposite direction because of the minus sign. You can put it this, okay. So I will not do this in detail. So it's similar relationship. I will, okay, this you complete by this is okay, current flowing through the I of S and potential developed across this. Current flowing through this you can find out. This is VC of S and SC. So you can complete this figure. Okay. So it is very important now to see that we must distinguish between these two formulas. Okay. One is indefinite integral minus infinity to t x of tau d tau is equal to x of S by S plus x of minus 1 of 0 minus divided by S, and another one is definite integral 0 minus to t x of tau d tau. That means you are neglecting this guy to 0, then it becomes x of S by S. So when you have initial charges in the capacitor, then you consider this relation. Okay, okay, which represents the initial charge across the capacitor or initial voltage, and this one no initial voltage. The second one indicates no initial voltage. So I will stop this discussion at this point. From this point onwards we will continue in the next lecture. Thank you very much.